Hi, I'm Sparrow, and I'm a science communicator with a background in behavioral science and pedagogy. Today's topic is Pangaea, but it's actually more than just Pangaea. It's also supercontinents in general, plate tectonics, continental drift, and even a teensy bit of speciation without dipping our toes into evolution, because that would make this way too long. Let's launch in. 3.6 billion years ago, a supercontinent which we named Valbara formed. Now, Valbara was east-west oriented, which we'll get into why that matters later. And that's just about all we know about it. Around 2.8 billion years ago, Valbara sort of broke apart through a process called rifting. Those continents that were formed by rifting proceeded to drift and eventually reformed into a new supercontinent, which we named Land around 2.7 billion years ago. 2.1 billion years ago, Land also broke up, or rifted, and drifted around until it formed Columbia, also known as Nuna, around 1.8 billion years ago. 1.5 billion years ago, Nuna broke up and proceeded to very rapidly form, break, and form into two more supercontinents. The first was Rodinia, which lasted from 1.25 billion years ago until about 750 million years ago. And the second was Pangaea, which lasted until about 600 million years ago. Once again, Rodinia and Pangaea were east-west oriented. After Pangaea broke up, the continents drifted around some more and then formed into a north-south oriented continent, which we named Pangaea. Pangaea lasted until around 300 million years ago before breaking up and forming the continents we have today. Now, as a kid in school, one of the evidences we learned about for Pangaea was, check the name so I make sure I say it properly, Lystrosaurus. A dinosaur. Now, I don't know about you, but I had a dinosaur phase as a kid. Unfortunately, my problem with dinosaurs was my same problem as I had with Pokemon, which was I had a really hard time understanding that the name of the dinosaur was of a species and not an individual. We had learned about the Lucy fossil, and I had assumed as a kid that every single fossil ever found was exactly like Lucy. One unique, special individual that changed everything we knew about science. So when I heard that they found Lystrosaurus on Africa, India, and Antarctica, I didn't understand what that meant. Kid me thought that meant that Lystrosaurus's butt and tail were in Africa, his rib cage was in India, and his head was somewhere in Antarctica. I was like, wow, that's a big dinosaur. That was it. That was my whole thought on the matter. And it never occurred to me to question it until I was making this video, which kind of goes to show how easily a little misunderstanding can spiral out of control if you don't think about what you think. But in doing my research, I found that obviously there wasn't some giant dinosaur so big it spanned continents. Instead, Lystrosaurus, the species, had individual specimens found in Africa, India, and Antarctica, which is actually way cooler when you know what that means. I mentioned before that unlike previous supercontinents, Pangaea was north-south oriented. The reason this matters is because of the way climate works on our planet. We have longitude lines, which go up-down, which determine kind of what time it is. You have your international date line, and then each time zone after that. Latitude, however, help us determine how far away from the equator, which the equator is closest to the sun and is always in roughly the same position compared to the sun throughout the year, despite the tilt of the Earth's axis. And each latitude line determines how much farther away from that equator you are, which indicates pretty measurably how much variance there's going to be in your climate. So if you live someplace like Alaska, which is very far away from the equator, you're going to have a lot of variance. You're going to be having extremely short days and extremely long days, and you're going to have very harsh winters and very opposite summers. In terms of entire continents, though, this creates different ecological niches, which are little habitats. Now, if we jump back in our minds to the origins of the whole theory of evolution, we look at Darwin's stuff, and we really simplify it because we don't want to get into evolution in this video, it would be way too long. What he basically said was, finch with big beak eats big seed, finch with small beak eats small seed, finch eats seed, size match beak. And that is perfectly accurate enough for what we're going to be talking about today. There are no universal species naturally occurring on this planet other than humans. And that's because humans do something no other species does. We modify the environment completely to suit our needs. Every other species finds an environment that suits their needs and stays there. The species we have on the planet today that are over multiple continents are ones that humans have taken and moved and modified. As an excellent example, let's talk about dogs. This little unwilling volunteer is Tayaki, and she's one of my pups. She's the baby of one of our rescues. And she looks nothing like a wolf. That's because over the 10,000 years or so since humans domesticated wolves, or 30,000 years depending on which group of humans you're dealing with, we made changes based on what we wanted these dogs to do. And of course, Frenchies in particular, we wanted to be cute. But before that, we needed them to have big ears for listening around for mice. We needed them to have small faces and eyes that would look towards our eyes and listen to what we say. Good girl. They didn't need tails or lots of endurance, Frenchies specifically, because they weren't going to be running for miles and miles. They were going to be sitting at our feet in lace factories, listening around for mice in order to get them so that they wouldn't tear up the lace. Other breeds of dog, like the German Shepherd or the Border Collie, have different adaptations that we bred into them in order to facilitate our use of them as herding animals, as sleigh dogs, as hunting dogs. We have dogs that were used in war, dogs that ran alongside fire trucks and warned people before we invented sirens. And basically anything humans do, there's a dog for that, because we made them. And so as a result, dogs are on all of the continents except Antarctica. However, in nature, without humans meddling in things, there's no species that's going to be identical on every continent, because every continent has vastly different climate zones, different terrains, and different habitats or ecological niches. So when we see a sample of a species that is identical, existing both in the African savanna and the sort of tropical monsoon zones of India, as well as the frozen wastelands of Antarctica, what that tells us is that those places weren't always that way, and that at some point in time, those places formed the sort of niche or habitat that would support the life of a critter like Lystrosaurus. Lystrosaurus wasn't the only one. There were also fossilized plants, which were sort of like fern tree things. And across different continent groups and different areas, we find other animal and plant fossils that indicate what sort of climates they had. Another evidence of Pangaea that I totally missed as a kid, but which fascinates me as sort of a rock nerd now, behold my crystal, is that we can also tell where magnetic north was at that time. And it's actually a really cool process. See, when igneous rocks specifically form, what happens is molten rock or magma underneath the surface comes up to the surface as lava and then eventually cools and hardens into regular old rock. But most rock, if not all, has magnetic compounds in it, usually iron related stuff, but there are other minerals which also have magnetic properties. And those, when rock is a liquid, are free to move. And so naturally they will move and orient themselves north-south. Then when the rock cools and hardens, they can no longer move. So if you take the rock and you rotate it, then your north-south is still pointed where it would have been if you hadn't rotated it. So the head of my little beetle, if that's north, well, as Pangaea breaks up, our north is still over here, but the head of the beetle moving tells us, well, this used to be pointed over here. The third evidence of Pangaea that I actually learned about on social media, completely out of context, is the Appalachian Mountain Range. Now, I don't know if you're familiar with all of the sort of urban legends, myths, and such of the Appalachians, but it's considered to be basically like the hauntedest mountain range ever. And people talk about it being super like spooky and haunted because it's super old. And I was like, okay, yeah, mountains are all old, like whatever. But when I was doing my research on Pangaea, what I found out is that the Appalachian Mountains are older than trees. When Pangaea first formed, the plates that sort of mushed together to make it created what's called an upthrust mountain range, which is the edges hit and they go crunch. As opposed to volcanic mountains, which are formed at subduction zones, where the edges go like this and then this melted lava pokes back up, or which form at rift zones like Hawaii, where the edges come apart and the magma turns into lava and floats back up and creates a mountain. So these upthrust mountains formed by crashing and the formation of Pangaea are so old that they formed before trees ever grew, and they formed before life walked out of the ocean onto land. That is so incredibly old that I can't fully wrap my head around it. In addition to them just being old, just saying that, we can tell by the mineral composition of the rocks and other geological factors that the Appalachian Mountains and the Scandinavian Caledonites are the same mountain range. They're on the same plates, or were on the same plates before, of course, those broke in a different direction. And they're the same mountain range that were formed at the same time. And even kind of cooler as an add-on to that, the current mountain range of the Himalayas is formed by the same processes, though different plates and at different times, as the Appalachians were formed. All of this was just super radical to me. And I got super deep dived into it and spent like 3 extra days just going down various rabbit holes about what Pangaea was like because I was so fascinated. The point of this video isn't just Pangaea, it's more what we've learned because of Pangaea. And to talk about that, we're going to do a teeny bit more time travel, but we're not going to go nearly as far back. We're only going to go to 1596 because we're going to talk about a guy named Abraham Ortelius. He was the first dude to say, like, hey, I think the continents are moving. And he was like, you know, if I'm right that the continents are moving, then maybe they used to be stuck together. I mean, they kind of look like they'd fit. At that point in time, people were just like, oh, okay, dude, sure. But almost 300 years later, in 1912, Alfred Wegener, who gets a lot more credit when it comes to Pangaea and continental drift, reframed that hypothesis with some evidence. He took some mapping data, he looked at different rock formations, he looked at different plants in different areas, and he was like, actually, this Abraham guy wasn't a complete idiot. This kind of makes sense, and here's why. In 1912, he published some papers about it. In 1915, he took his writings and he put them together into a book. And in 1920, when that book was republished, translated into various languages, including most notably English, the term used for his universal continent was Pangaea. Now, when he published this, he drew the attention of some very powerful people. The American Association of Petroleum Geologists. Which, I was like, why would they be interested in Pangaea? And the answer is because Pangaea is where coal and oil for gas and natural gas and most of the electricity on our planet, even to this day, all comes from the ancient peat bogs that formed on Pangaea. And what the American Association of Petroleum Geologists realized was that by better understanding continental drift and the history of our planet, they could better predict where they would strike oil and get more money with less expenditure. And so what they did was they said, yes, let's research this and we will help pay for it. Arthur Holmes proposed plate tectonics. He proposed that the reason that the continents moved was that the continents were on top of these plates of rock that could move around on the Earth, and he further proposed that the reason they moved was because the hot magma underneath, that liquid rock, was experiencing a convection effect. Now, if you're like me, the term convection is associated in your mind with a convection oven for baking fancy desserts. And so it might be a little hard to picture liquid rock convecting. But what it means basically is that there are currents of heat sort of moving around through it in sort of randomish patterns, allowing the heat to permeate throughout all of the magma. And if magma is full of these heat currents, then it follows that the magma would move and the rocks on top of the magma would also move around. He added evidence to this, and post-World War II, he included mapping of the ocean floors. Post-World War II, Arthur Holmes added more information to support his theory of plate tectonics. See, Alfred Wegener proposed a hypothesis. He had some evidences, he had some ideas, but what he didn't have was predictions. Whereas Arthur Holmes had more evidence, a more refined and specific idea, and he had some predictions for what you would see if it was true. And one of those predictions was oceanic rifting. Basically, if the continents are moving apart, then if you go in between them at the apart-ifying points, you will eventually find a place where the plates are coming apart and magma will be coming to the surface, becoming lava and solidifying. And post-World War II, as the US government became interested in mapping the ocean floors, both for war reasons, like, submarines, and for science reasons, they found that this was absolutely the case. Holmes also invented radiometric dating, which, when you learn about evolution topics and fossils, you hear about radiometric dating, or specifically radiocarbon dating, where we look at the way that these molecules throw away electrons and become other stuff, and we can judge how old it is. Using radiometric dating, which he used, I believe, uranium, he was able to pinpoint how old certain rocks were and therefore use their magnetic north of the rock to determine what orientation those rocks had during Pangaea. And then he quite literally wrote the book on how to do geology, because he was the globally recognized expert on the topic. But that didn't mean he knew everything there was to know. In fact, even today, scientists don't know everything there is to know about how plate tectonics work. We know some stuff, like we know that the oceans are spreading. We know that there are plates and faults, which are the edges of plates where they meet each other. We know there's a crust, a mantle, the outer core, the inner core. We know that continents drift. We know there are convergent, or coming together, and divergent, or spreading apart, zones. We know that some faults are what they call transform, which means they slide alongside each other parallel. We know there are upthrust mountains and subduction zones, which are places where they crash together and go up, or crash together and go down. We know those things that we can observe. We've also been able to measure that the crust under the ocean has silicon and magnesium, whereas the crust under continents is silicon and aluminum, or aluminum, depending on where you live. But we don't fully know why. And so I wanted to briefly go over all of the ideas that people have had for why all this stuff might be. So one of the early ideas that was floated, it'll be funny in a second, as to why plate tectonics works, why things are moving around, is because the mantle is liquid and the crust is solid, and so it probably just floats on top like a boat. Another idea was heat dissipation. Since the mantle's hot and the crust cold, then it must make it really slippy, sort of like a hot knife through cold butter cuts a lot easier than a cold knife in cold butter. There was an idea of density variance. Because different minerals have different densities based on their atomic weight, then maybe the heavy minerals are kind of pushing down in the magma and the light minerals are kind of pushing up, and it sort of stirs it about. Another idea was plumes, or like mantle blisters, as they called it. Like, oh, there's probably like really hot pockets of magma within the hot but not quite as hot magma, and it like shoots up like a geyser sometimes and shoves the plates aside. People thought there were mantle rivers, like little currents running through the magma of even liquidier magma that pushed the plates in certain directions and pulled them in others, that maybe looked similar to rivers on Earth. Some people suggested that it was gravity, that plates are trying to fall or slide downhill away from their source of magma, and then more magma becomes lava and piles up and builds that hill. People thought maybe it's the rotation of the planet just spinning it around like a giant centrifuge. That one we know for sure it's not. They were able to do some experiments and proved, like, no, if the Earth's spin was gonna fling the plates around, we'd all be getting flung too. People thought maybe it was tidal drag, which I was like, what? Does that mean the ocean's pulling it? No, it doesn't. It means the sun and moon, which we know do pull the ocean, pulling it. People said, well, we know that the moon pulls the ocean. We know that the sun pulls the Earth. And we know that our Earth isn't a perfect marble. So maybe these big things that already pull stuff here are also pulling at the plates and helping them move around. And scientists, in all of their experimentations over the past few hundred years, haven't been able to definitively say which things contribute how much. But they have been able to show that most of those things do something to do with plate tectonics. Now I'm going to glance over my notes again to make sure I didn't miss anything, because I know this is a lot. And I want to make sure I covered it thoroughly without going too long. And the answer is I did miss a little something. I missed the climate impact. So I talked about the climate impact as far as like latitude lines, but I didn't talk about the way that the plates themselves being mashed together or separate apart contributes to a global climate change. And I think, since I'm already at the 28-minute mark, that I'm just going to hold off on that and bring it up again when I do a video on climate change itself. So, if you like my video, please hit like, please subscribe, please leave a comment, and please tune back in next week for our next topic.